So let's summarize what we've learned in this module. This module has been an introduction to statistical inference. Okay, so the two types of inference procedures in this course are confidence intervals, which we kind of just talked about, and hypothesis tests. The goal of a confidence interval is to estimate a parameter value, such as a population proportion or population mean. The goal of a hypothesis test is to test a claim about a parameter. Both types of inferences are based on sampling distribution of sample statistics. For both, we report probabilities that state what would happen if we use the inference method many times. So more specifically, let's talk about confidence intervals. The purpose of a confidence interval is to estimate a population parameter on the basis of a sample statistic. Sample statistics vary, so there's always error in our estimate, but we will never know how much. We therefore use the standard error, which is the average error in our sample estimates, to create a margin of error. The margin of error is related to our confidence that the interval contains the population parameter. So like we talked about on a previous page here, let's see. Yeah, I think on the previous page, or was it the one before, they said, so in this situation, everything's centered around 0.60. I think that was the number of or the percentage of women in college compared to men, 60%. And then our interval here is between 0.5 and 0.7. If you're looking at specifically, for example, 0.64, that is within the margin of error. So that one is green because it's in there. 0.57, same thing. 0.57, so it was green, but this number is not in there, 0.72. That's too large. It's not within there, which is why they made it red. So I think we saw this before, but it's worth repeating. When the margin of error is two standard errors, about 95% of confidence intervals contain the population proportion. So let's see. We'll move this down a little bit. Okay. We investigated the 95% confidence interval for a population proportion in depth. When a normal model is a good fit for the sampling distribution, a 95% confidence interval has a margin of error equal to two standard errors. And we've kind of whittled it down to this formula here. The p hat plus or minus 2 times the population proportion multiplied by 1 minus the population proportion over n, which is the sample size. We say that we are 95% confident that the calculated interval contains the population proportion, meaning that 95% of the time, these intervals all actually contain the population proportion, and we will be right. 5% of the time, we will be wrong. We can never tell in a confidence interval, we can never tell if a confidence interval does or does not contain the population proportion we are trying to estimate. Now, on the other hand, hypothesis tests, okay. The purpose of a hypothesis test is to use sample data to test a claim about a population parameter. We investigated testing a claim about a population proportion informally. We make a claim about a population proportion. From the claim, we state an assumption about the value of the population proportion. Could the data have come from this population? Or is the sample proportion too far off? It depends on how random samples from this population vary. We construct a simulation or a normal model to represent the sampling distribution that occurs when sampling from a population with this assumed value. We make a judgment about whether the data is likely or unlikely to occur in the sampling distribution. If the data supports our claim, it is unlikely. If the data supports our claim and is unlikely, then we doubt our assumption about the population proportion. So for example, if last year 20% of the US adult population smoked, we might claim that the percentage of smokers in the United States this year is greater. So in the simulation, we set p to equal 0.2 and see if the data causes us to question the claim. If a sample proportion is likely to occur in the sampling distribution, then the sample result could have come from a population with the assumed value. In this situation, the data do not lead us to doubt our assumption about the data, do not lead us to doubt our assumption about the value of the parameter. We therefore conclude that the evidence from the sample is not strong enough to support our original claim. In our example, a sample proportion that is likely to occur means we do not question the assumption that we made when we set p to equal 0.2. We cannot conclude that the percentage of smokers in the United States is greater than 20% this year. If a sample proportion supports our claim and is unlikely to occur in the sampling distribution, then it's unlikely that the sample result came from a population with the assumed value. In this situation, the data lead us to doubt our assumption about the value parameter. Okay. That's okay. Sorry about that. All right. We therefore conclude that our evidence from the sample is not strong enough to support our original claim. In our example, a sample proportion that is likely to occur means we do not question the assumption that we made when we set p to equal 0.2. We cannot conclude that the percentage of smokers in the United States is greater than 20% this year. If a sample proportion support our claim and is unlikely to occur in the sample distribution, then it is unlikely that this sample result came from a population with the assumed value. In this situation, the data lead us to doubt our assumption about the value or the parameter of the parameter. We conclude that the evidence from the sample is strong enough to support our claim. In our example, a sample proportion that is unusually large means that the data makes us doubt the assumption that we made when we set p to equal 0.2. We therefore probability greater than 20% this year. I guess that should say, we therefore assume the probability is greater than 20% this year. Likely or unlikely. It depends on how much the sample proportions vary. If the normal model is a good fit for the sample distribution, we can calculate a z-score and use an applet to associate a probability with our likely and unlikely statements. Recall what we learned in the distribution of sample proportions to calculate a z-score. Just to remember the formula again, the standard error is equal to p, the square root of p times 1 minus p over n. And then the z-score is the statistic minus the parameter over the standard error, which I think I should erase because you can't see anything. There we go. Yeah, this is two different formulas, but it's kind of hard to separate them. I don't know why they're so close together. Anyway, there's one here for the standard error and one here for the z-score. But if you kind of put them together, the standard error is the square root guy. If you put that square root guy in the denominator here, because that's, yeah, that formula has the standard error in its denominator, p hat minus p over the standard error, but I'm just replacing it with what we know to be the formula for our standard error, 1 minus p times p under a square root multiplied by n under the square root. Okay, so that's our z-score. We can also write this as one formula instead of two separate formulas.